Okay, so let's pick this back up. This is showing you the S-cis conformation. We already talked about this. Your diene's got to be in the S-cis conformation. It does prefer to be in the trans. So you can see the equilibrium prefers here, but there is some rotation. And once it does rotate, and the rotation really is dependent on these two groups, the size of these groups. All right, obviously the bigger these groups are, the less likely this is going to want to be in the S-cis conformation. So it is based on sterics. Okay. So heating the reaction is what sometimes speeds up a Diels-Alder reaction. You'll actually see Diels-Alder reactions done under heat so that you can get into this S-cis conformation. Okay. So here it's just kind of showing you rates. All right, showing you the rate of Diels-Alder reaction compared to the dienes. All right, this will not do a Diels-Alder. Okay, why will this not do a Diels-Alder? Well, it's because these double bonds are locked in an S-trans conformation. This is kind of how they proved it's got to be an S-cis. This will never go into an S-cis, so because of that, you can never do it. All right, this obviously is going to be the slowest because you have two incredibly huge groups next to each other. Okay. All right, so the cis, you notice that that's a cis and that's a cis. Here you have the trans, you know, that will go. All right. And then obviously this will go faster because your two larger groups are further away. And then if you have it tied together, if you have it locked in, obviously this will never go into an S-trans conformation. It will always be in an S-cis. So that's why that will go the fastest. Okay, so cyclopentadiene, which is this, undergoes a Diels-Alder reaction readily because of its fixed S-cis conformation. When the diene is sterically hindered, the reaction slows down, even though the conformation can be S-cis, and S-trans dienes cannot even do Diels-Alder reactions. Okay, let's do more stereochemistry, because I am sure that the 2 slides ago, it hopefully made somewhat kind of sense, but like I said, we're going to talk more about this in class. There are some really cool videos that we'll watch on Khan Academy. They actually go through it very well, where he draws like the diagrams, but it's a lot easier if we just talk in class and you can get all your questions answered. Okay, so they show you the stereochemistry. They're also showing you that if you start with cis on your diene, you're going to end with cis on your diene, because this bond does not freely rotate. Okay, if you wanted trans, then you just go with the trans dienophile. Okay, if you have a triple bond, you can end with a single bond. I'm sorry, if you have a triple bond, you end with a double bond right there. Okay, so these are all Diels-Alder reactions. Remember, you're forming bonds. Your bond you're forming is here. That's where your 6-membered ring is coming from. Okay, so those are just some examples. Okay, so the endo rule, which gives rise to secondary overlap. This is what I was talking about. Secondary overlap. Okay, so the picture we saw was all the orbitals here, all right, and I showed you that you either have 2 groups here which are sticking out, all right. This is my dienophile. I'm sorry, my diene. This is my diene. Okay, all right. You want the electron withdrawing group, this is the electron withdrawing group, to be underneath so that it interacts with these pi bonds. Here it's showing you this pi bond right here. Okay, the pi bond between your carbon and oxygen is this pi bond right here. Okay, you want this to kind of overlap. It's kind of like holding extra hands, an extra pair of hands. You want these orbitals to overlap with these. See how they're, that's what's called a secondary overlap. Okay, to kind of hold it in place, kind of holds it in place. You can kind of see the bridgehead is starting to kink out. So you want the electron withdrawing group underneath, and you want the 2 non-electron withdrawing groups sticking out. The other conformation, maybe I should draw the other conformation just to show you what the difference is. Now I'm going to try my best, so just hang in there with me. Like I said, we'll talk more about this in class. So that's your diene, your blue diene, but then rather than having the oxygen sticking underneath the cyclopentadiene, you have it sticking out of the cyclopentadiene. Okay, so notice here's my diene. Okay, notice this time the 2 hydrogens are underneath my diene, and the electron withdrawing group is sticking out from the diene. Here's a diene, it's sticking away from it. It's not underneath it. These are underneath it. This is outside of it. This is underneath it. So this is what you want. This is what the secondary overlap occurs, is when that group goes underneath it and can actually form these pi bond overlaps, which is what's called the secondary overlap. Okay? And this is what's called the endo rule, because your electron withdrawing group goes down, which is the endo position. So if you look at one of these compounds at a side view, you got groups going down and going up, going down and going up. Let's kind of get that there. All right. These positions down here are the endo positions. The groups that are coming up like this are what's called the exo positions. Okay, so you got endo and exo. So this is called, let's put the double bond there to show you this. So this is called the endo rule, because the groups prefer to be in the endo position because of that secondary overlap. Okay, like I said, if you get this, if you're sitting there saying, oh, I can see it, great. If not, don't worry, we will talk about more about it in class. All right, here are examples of endo rules. All right, so this is kind of the one we saw. So taking this, reacting with this. Remember, this kind of has to flip over so that this group can maximize and overlap underneath here. Same thing here. This group is kind of coming down in the endo position. Remember, the endo is the down position. The exo is where these are going up. Okay, so remember, this hydrogen and this hydrogen are in the exo position. Right? This one right here and this group right here are in the endo position. Same thing here. This hydrogen and this hydrogen are the exo. This whole entire group down here is in the endo, because you get that secondary overlap. Okay. Now there is a way to actually alter this if you wanted to. If you wanted to get more exo product, there are ways by cooling down the reactions and adding a catalyst and things like that. We're not going to go over that in this class, but in case you're curious, there are ways in order to get the exo products. But the endo is the favored product. All right, this word, norbornene, that's this kind of a system. That's the nomenclature for this type of a ring where you have, it's what's called a bicyclical compound, or let's just say, yeah, cyclical. All right, where you have a 6-member ring. So notice I have a 6-member ring, and then I have this other bridgehead. That's what's called a bridgehead right there. All right, what happens if you have unsymmetrical, or not unsymmetrical, but if there are two possible ways that your products can form? Notice I have a group at the 2 position here and a withdrawing group. So the question is it reacting like this, or does it react like, I'll draw it over here. Like that. Is our withdrawing group, or our W group, on the same side of our D, or is it on the opposite side of the D? Well, obviously it's showing you it's on the opposite side of the D. So if you have this kind of a compound, starting materials, you always form the 1,4 product. Okay, it's 1,4 because if you count 1, 2, 3, 4. Okay, and the reason is because it kind of shows you kind of a resonance reasoning why it's based on electronics. If you have a donating group, all right, these electrons can push in and kick these electrons out on this carbon. Okay, thereby, so this structure refers to this structure, putting a negative charge on this carbon. So in a sense, you have a negative here, a partial positive here, a partial negative here, and a partial positive here. Okay. Now, if you look at the resonance of your diene, or your dienophile, sorry, the resonance of your dienophile, so this can pop to here, that to pop to here, putting a plus charge here, partial minus charge there, partial positive there, negative there. Notice that this negative side, this negative carbon, is attracted to the positive carbon. This negatively charged carbon will not be attracted to this partial negatively charged carbon. So if you had this kind of a system, you would be having a negative charge here with a partial negative charge here. All right, negative does not attract to a negative. This carbon down here is the partial positive. This would be more attracted to this carbon. So that's why this wants to be flipped upside down, where your withdrawing group is on the bottom instead of on the top. Okay, so it's based on the electronics. So the 1,4 product is formed. This compound is not formed where the D and the W on the same side. Okay, now what happens if the D is at this position instead of the 2 positions at the 1 position? That's what this page is about. Well, now it's the opposite. Now your D and your W want to be 1, 2 from each other rather than 1, 3. So that does not happen. And the reasoning is exactly the same thing. Okay, you have the electrons pumping in, all right, putting your negative charge here, all right, putting a partial positive here, partial negative here, partial positive there. Same thing is here. This is your partial positive, partial negative. Again, your negative is attracted to your positive. Your positive is attracted to your negative. It just flip-flops it depending on where your D is. Okay, so if your D is on the second carbon, right here, okay, the W wants to add this way. All right, 1, 4 opposite of each other. If your D is at the 1 position, your W is going to add right next to it to give you that product. Okay. So here's kind of a practice problem. Predict the products of the following proposed Diels-Alder reactions. So as soon as I count to 3, turn off the video, do the problem, and then come back for the answer. 1, 2, 3. Turn off. Okay, welcome back. So we have, here's our diene. We have a group at the 2 position. Here's my electron withdrawing group. All right, that and that. That's where it's going to combine. The question is, does this group want to be here, or do I want to add it? Oh, let me erase that. Or do I want to add it like that? Okay, which one of these? In reality, let's actually go through this and just kind of combine everything. It actually wants to add like this. It wants to come because this electron, right? So here, the CH3. Forgot the CH3. Right? Because you want the secondary overlap, you want this to come underneath here. But the whole point is that this group wants to be opposite. So your product, the way I would write it, just in full glory, the way I have it written with all the correct stereochemistry and all that, would be like this, with your dotted line CH3 and your hydrogen coming out. Okay, so that's how you would want it. All right, here is the solution. Sorry, my answers are over it, so let me just kind of erase. But it shows you that the major product, this one right here, is that one. They don't show stereochemistry here, but technically, since we've talked about it, that's really where the stereochemistry is. All right, here's another problem. Once I count to 3, turn off the computer, or sorry, the video, and do the problem. 1, 2, 3. Welcome back. If you didn't do it right now. And in this case, you have a 1 case. All right, so this time your electron donating group is here. So remember, your electrons pump in, all right, to kind of make the negative charge here. All right, your positive is going to be on this side. So you want these to be attracted to each other, so this has to flip up. So the correct structure, I'll draw it up here so we don't go over the answer. CH3 with your CN. Now, we didn't talk about this, but your stereochemistry of this, let me talk about the stereochemistry of this. CN. Okay, they're actually going to be cis, because if we, let me try something here. Let me try to do the, and then your double bond CN wants to be right there. You have an H here. I know this is absolutely horrendous drawing. I am trying my best, guys, but like I said, this is for the basic ideas. You want to get 90% of the information from the videos, and then the details we get in class once we come to class. Trust me, I will go over this more, but just to give you an idea. There's your secondary overlap. These are going to be 2 from each other. All right, now if you can visualize this, once this goes underneath it, this hydrogen and this hydrogen are going to be on the same side of each other when you form the bond. When you start forming the bond, these are on the same side. Some people can see this in 3 dimensions, some people can't. And then these two groups, so your product is actually is going to be cis. You actually have a cis product. Okay, I don't know if the answer of this tells you that, but we will talk more about this in class. Okay, well, they actually do show you it's cis, so I'm glad they did. You can see that the two compounds are cis to each other, and it's the 1,2 product. I care that you understand more it's the 1,2 compound. If you can see why it's cis, that now puts in that overlap part that we talked about.